So we have inside OrcaHub 2 of exercises that we have put together. So far, we have 23 people joining the session. So let me show you what we're trying to do with the session today. The idea is to use pretty much a DCA, and use a well type curve, and from 3 wells. So I'm going to go through a process of visualizing those wells, normalizing that data to a common date, and then creating an average profile to later on create a decline curve analysis for those wells. There is this exercise, the first part, it's going to take a bit of time. We're going to build everything from scratch, and I'm going to show you a bit of what I'm trying to do with the plotting as well. We also have another part of exercise in which we will create, with using a Arps equation for horizontal wells. We generate a range of initial rates, and we are going to generate a probabilistic forecast for that initial rate, and also we will combine with a DCA. So it's going to be a bit of an interesting exercise for this one. And hopefully you can link both exercises. You can see what is more or less what is the criteria or what we're trying to do by generating a well type and then later on doing a probabilistic forecast. So I hope everyone is related already to OrcaHub. And in OrcaHub, we have a couple of exercises that are published already on the DCA folder. So I'm going to put it in this chat for you to have a look. And I guess at this point you should be able to go and clone the repository. So the exercises that we will be doing are, if you see the history, the most recent ones are the DCA probabilistic and the DCA well type. So the solutions are already there, and if you are a bit lost on what I'm trying to do, I would recommend you to have a look at the exercises here. Hopefully they should be published. I published them just a few minutes ago, and you should be able to look into those. Let me see. Yeah, so they are all here. So we're going to try to build everything from scratch. As I mentioned, I'm going to try to write everything that you see in that book from scratch. And this is my DCA well type. So first thing that I'm going to do is, let me just do something here very quickly. Right. So first, what we want to do is, as you know, I'm going to just start by importing my libraries. So, and the libraries that we will be using here are the usual suspects. Notice that I have selected Markdown, so when I run this, it's a title. So the libraries that we will be using here are the NumPy. I think we will use NumPy a bit, yes. And we will use it as usually people with a pseudonym EMPI. And we will also be using pandas. And in addition, we will be using the library for plotting Matplotlib. So I'm going to use import matplotlib.pyplot. as PLT, right? So I have my libraries imported, and I'm going to leave some spaces here for my general functions. So just going to write here a markdown where I will put general functions that we will use in a bit. No, someone is knocking the door. This is, so there you go. Okay, so the general functions, what we're going to do here, first of all, I would like to generate a function where I can explore the data, where I can see what it's on that file. So first of all, let me start later on this line. I'm going to write my, let's say, main section. It's a main section of the notebook. And this it's markdown again, right? And what I'm going to do here is read the Excel file with the data that I'm going to be showing you during the session. So if I go to the folder and show you what it's the file about, let me open it just a second. I'll move it to this side of a screen. So I have a series of wells with an oil rate. I have in this file well W0, W1, 2, 3, 4, and 5. And we want to analyze a bit the file and understand which wells we're going to be using to generate a generic well type. The purpose of these sessions are not to go into the technical details. However, if you have questions, I should be able to answer some of those. So first of all, let me open the file. I'm going to import the file. Remember that in order to import the file, you need to use your pandas library. So I'm going to do pd dot read Excel, and let me open the file that it's called well type. I think I'm going to open the file called well type only on read mode. And the sheet name for this file is just sheet 1. So if you remember from previous sections or from the previous session, we can have a look at the header of the file. Let's have a look at the F5 header. So this is exactly what I was showing you in the Excel. So we have a column with the well name, the date, and the oil rate. This is a little interesting because in the previous session we have the Excel order in a different way. We have date, we have well name, and with the rates for every one of the wells. So this is a bit of a different way in which you sometimes can find the data. And it's actually a very convenient format to work with tools like Power BI or Spotfire. Right, so if I want to know which wells do I have there, so if I want to access just the column wells, so I can do df well, and yeah, that's very convenient. I can see all the wells there. But of course, I want to see exactly the unique number of wells. So the only thing that I have to do is type unique. And there you go, you have the unique number of wells that I have in that Excel. So next, I want to produce a plot of date versus rate. So for that, I'm going to use my general function area. and I'm going to generate a regular plot function. So this is a function that I will expect to pass a data frame and a list of wells. That's what I want to pass here. So let's define the function. And the function it's going to have a, I'm going to use the matplotlib subplots. And for that, I can do things like the figure and the axis that I want are from the PLT library. Yes. So if I do tab, I'm going to go for the subplot, right? And I can do a plot. I want to add a label at the bottom. So my label is going to be just simply date. I want to make a plot of date versus rate. So my label on the y-axis is going to be rate. And the function will receive a list of wells. So what I want to do is for well in wells, I want to be able to plot every well as I go into this loop. Remember that I have here 6 wells, so I want to, for every one of those wells, I want to generate a set of points or lines. So I'm going to do df, I'm going to filter data frame by doing data frame. I want to only show the values where well is equal to well. So you can see that I'm using equal just to check. I'm making a comparison. I'm not actually assigning a value, so it's an equal. So if I show you again the Excel, this is equivalent to go through the Excel and start to filtering one by one W0, and then eventually getting a plot of W0, then W1, and producing a plot of W1. So that's what I'm trying to do there. And what I'm going to do is I'm going to store the rates of that filter data frame, and I believe the column for the rate it's oil rate with the units standard barrels per day, and the column for the date is data frame filter. I'm going to use date, right? So I'm going to plot here using axplot date, that rate, and I'm going to put a label of the name of a well by having the legend, the name of a well. Okay. So for the time being, let me return the PLT, the plot, and I have to notice that I have to run this line in order to use the function here later on. So let's call it plot underscore data is equal to regular plot, and I'm going to pass the data frame and the list of wells. In this case, I can let me store this in a list. I'm going to call it all wells. I'm going to call it all wells. need to run it again, and I'm going to use it here, all wells. So if I run that line, oops, something happened here. Arc support object is not iterable. PLT subplots, subplots. For welling wells, name wells is not defined. Oh, this is called list of wells. For wells in list of wells. Okay, here we go. So we have a plot. In fact, another thing that I want to do is make this plot a bit bigger. So one thing that I can do is specify what is the resolution that I want that plot on. So I'm going to do figure. If I'm not wrong, this is a fixed size, figure size, and I'm going to make it a bit bigger. There we go. Now, as pointed out in the previous session, or in the session that we had yesterday, discussing more general matters on the community, it would be great to put just points instead of lines, as later on we will do a fit. So I can simply go through the function again and specify that we want to have some dots in the plot. Okay, here we go. So far so good. We have a plot. The axis on the y-axis we have rate, and we have date on the x-axis. Right, and so let's say, oh, there is something that is not working quite nicely. As you can see, that I don't have a name of a plot. So what happened is with the label, I only got different colors, but I didn't get the actual labels of which wells I'm plotting here. So for that, I'm going to do an additional step here outside of the loop, of the for loop, which is ax.legend, and I think if I do that only, that should work. Let's see. Yes, that should work. There are some options that you can pass around here, like for instance, shadow equal true. So you can play around with some functions. Yeah, so you can see how now we have the legend. And we can also do, there is also something called fancy box. I don't know what that does. Let me have a look. Fancy box equal true. Well, it doesn't look that fancy, but yeah, it's all right. We have some options there. Now, what I want is to generate a plot of only these selected wells. So I want to later on, if I want to do, let's say that I want to do a well type of only the wells that have been producing after 2011. So these wells are well in the past, and probably I don't know the location of where the wells are located, but maybe they are not necessarily on the best place, or they are not necessarily representative of the well type that you want to use later on to do a forecast. Okay, so we're going to take W4, W5, and W3 as the selected wells. And this is where the function will come in handy, because I just need to do W4, W5, come on, W5, and W3. And I can do exactly the same plot data, regular plot, oops, sorry, plot data, regular plot, but I'm going to pass the selected wells instead. And here we go. Now, this is where I want to generate my decline curve analysis for the 3 wells. I'm generating a well type. But as you know, I need to make sure that all these wells are normalized to a common date. So I'm going to normalize it to a 0 day and use the number of days to make the forecast. So for that, I'm going to write a small additional function. Let's call that function, I'm going to do a function for the normalized plot. And this function will receive again the data frame and the list of wells that you want to plot. If you want to add and there is a question in the chat, if you want to add the units, well, you can, for instance, let's say you want to pass in the regular plot, you want to pass units, and of course, I have the units here just because the Excel, the column name is all rate STB per day, standard barrels per day. But let's say it's not, you don't want it like that. You want to the label here. What is the label? In the Y label you have rate. You can also say, let's say, rate loss. Let's put a space, and you want to pass those units names. I believe you can do this. And when you call the function, you can say, I want this in barrels per day, for instance. So if you do that, it's not going to work because I haven't run this yet. I need to comment this out for a second. But there you go. You have a rate barrels per day here, so you can pass the units as well and edit your plot as you want. So okay, I'm going to carry on with the normalized plot. And the first thing that I want to introduce a concept of dictionaries for this exercise. And let me do a small exercise here of what is a dictionary. Probably some of you already know what is a dictionary, but let's say I want to create a new dictionary. A dictionary, you can hold values, list, or arrays, or whatever object inside this object that is dictionary. Let's say, for instance, we have a dictionary. We're going to hold a list of members of the community. So let's say this is a tech members, right? So I can say, for instance, PEC members, I can say, for instance, I want to add a member called I'm going to add a member called Alejandro Primera, and this is a dictionary within a dictionary, but basically I can say very simple things like Alejandro Primera, and I'm going to add few characteristics about that person. So where country. Let's say we put country, and notice that I'm going to use the column, not the equal sign. So I'm going to say country, it's Venezuela, for instance. I'm adding a string there, and I'm going to add profession, and living a happy life, living a happy life, right? So if I do peg members, if I show you what I have in peg members now, I have my name, store, and I have a sub-dictionary with country, profession, and what is my profession. And I can keep adding more members to the PEC members community. So I can keep adding, as you can imagine, I can copy this and I can put John Smith, and this is from Wakanda, and his profession is save the day, right? So if I again call PEG members, I can call back to this one. So I have in the dictionary John Smith, Wakanda, and whatever. So the other thing is that you can save strings, you can save lists, you can save whatever you want in these lists. Okay. So sorry I diverted a bit, but I want to show you why I want to use or the concept of dictionaries here. And I'm going to create a dictionary where I'm going to store the normalized data. And in the dictionary, I'm going to iterate again for well in a list of wells. And what I'm going to do, again, same thing. First, I'm going to filter. I'm going to filter the data. But notice what I want is really to make a plot where everything starts from day 0. So I need the minimum date. What is the start? Let's say start time. And the start time is always 0, which is a minimum of the DF, the minimum of that date. Okay. So if I go back to Excel, for W4, this is my time 0. So I want that forecast, that date, to have a column or a list with that starts from time 0. And that time 0 should have an equivalent oil rate of 5,641 barrels per day. So far so good. And now what I'm going to do is my rates are exactly the same as before, DF filter. And again, it's oil rate STB per day. And now my time is going to be equal to the whatever time I have, DF filter minus that start time, right? And if you remember from the session that we had last week, this is probably in microseconds. So I need to convert this to days. And because it's a data frame, I can do the time.dt.days, convert it to days. Just small useful things. So now I'm going to use the full power of a dictionary, and I'm going to store for normalized data of that well. I'm going to store what am I going to store? First, I'm going to store the rate, which I have it. And I'm going to store the time, which is now in days. And remember, something, I'm going to make an error by, just on purpose. And I'm going to call that, I'm going to call this. I'm going to call that plot. So another plot, norm data. So normalized plot, I'm going to pass the data frame and the list of selected wells. And what happened here? Nothing, it seems to be happening here. Well, there is an error. Oops, there is an error there. Cannot operate timestamp, but receive a float. This is awful. For wells in wells. Oh, sorry. I should have put here date. And okay. So I run, oh, there is a missing argument here. Units, thanks, married at ppd, barrels per day, or STB day. And on this one, as you can see, if I run it, nothing is happening. So obviously I forgot to make the return of the function. So be careful when you put it. There is an indentation here, so I'm going to put it just here. If you put it here, you're returning at the end of the first loop. So you have to put it here. Return norm data. Oops. Did I run it? Oh, sorry. I want to normalize. This is just the normalized data, not the normalized plot. This is just the normalized data. So this is normalized data. Okay. So that normalized data, we will use it later on to do the well type. To do the normalized plot, actually, I'm going to speed this the section a bit forward. To do the normalized plot, similar to what I've done with the regular plot, it's similar. We're going to use the same concept of start date, which is the minimum of the date for a given well. Remember that we're taking the minimum of these values of a date. And then by doing the date minus that minimum, which is equivalent of, say, I want to do the minimum of this array, yes, and by doing the minimum, right? Oh, of course, because I have more wells, but because I'm using pandas, I'm filtering already I'm applying the filter to only that data to every particular well. So if I do a normalized plot now, and I'm going to call this normalized plot. There we go. So everything starts from 0 and up to whatever number of days the well have produced. And this should actually be called normalized data. And from the normalized data, I can get, for instance, the data for the well 4, and I can get only the rates if I want. So that's accessing data in the dictionary. Okay. So let me clear this output. And the next thing I'm going to do is produce a well fit for the average of this of the rate. So I need to add all those dates on a day-by-day basis, and I need to then average the dates and then fit a well type. For that, we're going to use a decline curve analysis with the Arps equation. Okay, this is not an unconventional well, so I'm not going to use one as we used the last time. And Arps is quite simple, and I'm not going to brag about remembering an equation by heart. I'm just going to copy and paste because I probably would make some mistakes. But in Arps, we have a beta factor, an initial rate, and a decline rate. And what we have the exponential, we have the hyperbolic, and we have the harmonic equations. So if the beta factor is 0, we are under the exponential scenario. While if we have values of between 0 and 1, we are in the hyperbolic scenario. So this equation is going to return the rates given a range of times in days, provided an initial rate, a decline rate, and a beta factor. So let's start to write an equation, and this is where it gets a bit more complicated because we are going to write the well type function. Okay, so let's just simply call it well type function. So in the well type function, let's call it well type. And in the well type, I'm going to receive the dictionary that we have created. So I'm going to call it new dictionary. I will select the wells that I want to use for the well type and how many months or how many points of data I have. Let's call it n months because effectively it's the number of months that we will need. So this is one way, very quick, in which I have put together the exercise to illustrate it. There are many other ways to do it. You can use pandas as well. I'm using a dictionary and I'm using a NumPy arrays to add up and do operations in this particular case. So my dictionary, my well type function, I'm going to tell you what I want to return. I want to return the fit, a dictionary with the fit values, the fit value of beta, decline rate, and initial rate. So I'm going to first of all say this is an empty dictionary, right? So I'm going to create an empty NumPy array with just zeros. So if I do empty zeros for a number of months, just to show you what this is doing, let me put this in here. So if I put a 10, So this is creating an NumPy array with 10 zeros on it. I believe you can do ones as well. You can do some other stuff here, but I'm going to use the zeros. I'm going to use the zeros here. And I want to get the number of wells that I ultimately will be using, which I know the number of wells for that matter. But let's say for wells, in wells. So first of all, I'm going to say my time. I have a time for the well. Remember that we stored it in the well as time. Yes, we stored it before. So if we store the time here for all the wells, and I'm going to do a trick here because I want to get the well with the most points to make sure that I always get the end of the NRI will have the same amount of points as the W4 well. But of course, I can put here something like len of norm data for the W4 well for the array time, and I know that it's 98 points that I have there. But I don't want to do that. I want to automate the process because I want to make sure that this code is able to be usable later on if I change the input Excel or if I change the wells that I'm selecting. So what I'm going to do, instead of doing this, I will do something like if len of the time is greater than time size, then time size, let's first define what is time size. I want to make sure that every time I go into the loop, I capture the time, the size, the number of points I have in the per well. So that time size is equal to length of time, and I want to assign something called the final time. So this is an array that I want to use for the forecast. Final time is equal to time. So that's only on that side. I want to also make sure that my production, I'm going to create a variable for temporarily storing the production, which is a new dict of that well, let's say for the well that I'm iterating here. And I'm going to get the rates. And I'm going to use this little trick of a month. Actually, I think, yeah, I'm going to use that same trick of a month to make sure that the array always have the maximum amount of points that I need, which is the n months. So a bit more of codes here. I'm going to replace the last values of the array, or the first values of the array, with the data. This is just to make sure that whatever let's say for the well W4, we know that we have data up to this point. But for the well 5, we don't have enough data. So if I want to add an NumPy array, so let's say I have an NumPy array, let's define A equal an MP dot array, and I want to put here an array that has 3 values, 1, 2, 3. And I have another array which is B, MP dot array, which has only 2 values, 1 and 2. So if you want to do C is equal to A plus B, okay? So this is telling you that you have an object of shape 3 or size 3, length 3, and an object of length 2, and it cannot be added. So what I'm trying to do automatically here with these MP zeros is effectively making sure that all the arrays have the same size, and I can do this operation at the end. So this is what I'm trying to do with this particular piece of code. By adding the remaining zeros to the NumPy array. So prod total, I'm going to keep adding the production at the end. So every time I go in, I will add the production of all the wells. And this is I plus equal 1. Okay. So if I want the average rate, prod total is equal to prod total over I. Oh, I didn't define I, sorry. Let me put here, this is actually the number of wells. So this could be length of wells. So I'm just making sure that I have, this is not prod total, this is production average. It's the production total divided by the number of wells that I'm using on the code. And now this is where we go back to what we did last time with the DCA. I think it was a multi-well. And if you remember from last time, we have the function here where the car fit function that we use to fit the production of the well. In this case, we're using Arps. So we can use return, let's say, top T and the covariance matrix that we are not going to use yet. And we need to use EMPI for fit, which I haven't imported here. So I can do from scipy.optimize import curve fit. There you go. So I can do curve. Oh, sorry, curve fit. Oh, I need to run this piece of code. Okay. So I can do curve fit. Now I'm going to use the Arps equation. The Arps equation that we define here. And I'm going to optimize for the 3 coefficients in R. First of all, I'm going to pass the final time, which is this variable that we are storing here. And then in the order of variables, I need to pass, B factor initial rate and decline. So let's pass here the factor. Final time, production time. So first of all, we need to pass the final time, the product totals. But I need to define the bounds of the B factor, the initial rate, and the decline. So I'm going to define first the lower values. So I'm going to start from 0, 0, 0 for the three of those. And for the beta, I know that beta could be up to 1. Well, there are scenarios that people model it with a higher value, but let's say that we want these wells. These are conventional wells. They are going to be declining, and we're expecting to be a maximum beta of 1. And we have also a maximum rate for those wells of, these are horizontal wells. Let's say that they can do very well, but we know that historically they can exceed 7,000 barrels. So I'm going to put 10,000 barrels. I don't know if later on we import some other wells. And I'm going to say that my daily decline rate, and be careful because this is daily decline rate, it's 0.1. Right, and this is where it comes a dictionary again. And I'm going to store, in fact, I don't need to use this in here. I can put it at the very end. I can say my beta, you have to put it in quotes, it's equal to what POP-T is returning in the first array. If you remember from the last exercise, from the basic exercise, this one, sorry, from let me see, from the DCA multi-well. If you remember when we did the curve fit, we had an array, and the array returned 3 values. In this case, are the 3 values for the Duong equation. They are coming from the POP-T. POP-T is returning the array. I can call this whatever I want. I can really call this. I don't have to call it POP-T. I can call it fit values if it's more helpful. So fit values for 0 is a beta. For initial rate, it's a fit values 1. So it's the second value of the array. And for the decline rate, we have fit values 2. Okay. Fit values. Okay. Sorry, I missed a couple of parentheses here and another one here to close the whole function. There we go. I'm going to delete this. I'm going to delete this. I'm going to carry on. So now I want to do a well fit. It's going to be equal to well fit function. Oh, sorry, well type. It's called well type function. And I'm going to pass the normalized data. So the normalized data we calculated before. It's where is it? Norm data. I'm going to pass that dictionary with the norm data. I'm going to pass the selected wells. I'm going to pass the number of months. Oh, number of months is not defined. Why is not defined? Okay, let's define it here. Number of months. Fit values. Beta fit values. Didn't like beta fit values 0. What's happening here? Beta. Name Arps is not defined. How is it called? Arps. Okay, so I think we have it already. There we go. So we have a beta coefficient, which is nearly 0 or exponential. We have the initial rate, which is actually 10,000, which is a bit strange, actually, considering that none of the wells are reaching the 10,000. I think we have to fix that in a bit. And the decline rate, which is a daily decline rate. So let's do something. I'm going to take, let's take a small break, and we can come back in about at 7:15, which is 10 minutes or so. Okay, so we'll fix the beta, we'll fix this issue, and then we'll do the final plot, and we will move to the next exercise. Meanwhile, if you have any questions, please ask. I'm going to be sitting here anyway, so I'm not going to go away, so you just keep asking questions on the chat or on the voice. Well, meanwhile, I'm going to just make a pause.